All right, guys, so where we're starting off is with this problem here. Now, we did this one yesterday. We solved this one yesterday. And when we solved this one yesterday, we found that x was equal to 0, x was equal to 2, and x is equal to -2, yes? And I said that -2 and 2 are repeated twice. Well, let's just go on and check it. Now, one way that we can kind of check solutions is, well, if it's a solution, it means it's a factor. If it's a factor, we learned the other week that if I use synthetic division on this polynomial, which we found out to be 2x to the 5th minus 14x cubed plus 24x equals 0, if we use it on this here, the remainder will come out to be what? 0, yes? Because if the remainder is 0, it means it's a factor. If it's a factor, it means it's a solution. It's one of the solutions if we solve for the value of x, which we did. So we have these here. I'm just going to start off with 0. So going across the top, we would have 2 for x to the 5th, 0 for x to the 4th, -14 for x cubed, 0 for x squared, 24 for x, and 0 for our constant term. So we had a few 0 values, and that's fine. Drop the 2. And luckily for this here, I mean, since the number inside the cubbyhole is 0, it's going to make this kind of easy, because 0 times 2 is 0 plus 0. 0 times 0 is -14 plus 0. It's going to be -14. 0 times -14 would be 0. 0 plus 0 is 4, 0, and 0. That's kind of like what we expected, yes? Because we expected a remainder of 0 because we know it's a solution since it crossed the x-axis, yes? Now, this is something a little bit new. I got straight into it with the other hour. Now, we started off with a degree 5, yes? If I were to put the variables back in, we'd have our constant term, our term with x to the 1st, x to the 2nd, x to the 3rd, and x to the 4th. We decrease the polynomial by 1 degree, yes? Is there anything that says that I can't use synthetic division off of what we just got here? No. So if I want to, what I can do is I can set this back up, and not using what we started with, but what we just got, 2, 0, -14, 0, 24. Let's use 2. Because if these 3 here, we said they were factors of the original polynomial, yes? Well, if it's factors of the original, it has to be factors of anything we get from the synthetic division, because it's still part of the original polynomial, yes? Because this here, if I'm going to write this out on the whiteboard, because what we just said was just x minus 0 is being multiplied by 2x to the 4th plus 0x cubed minus 14x squared plus 24. So those other factors we got are really coming from this thing here, yes? Well, yeah. So I can keep doing synthetic division to this over and over again. So we can do it with 2. Well, 2 times 2 is 4. I hope it's okay that I'm not writing out the multiplication on the side. Yes? Well, 4 plus 0 is 4. 2 times 4 is -14 plus 8. -6. 2 times -6. 0 plus -12 is, and 2 times -12 is negative, which would give us 0. So again, it's saying that's a factor, yes? Well, we already knew that, correct? Okay. I'm going to do it again with -2, but again, I'm just using what we got from the previous one. 2, 4, -6, -12. I'm going to put kind of a dashed line to separate this here. 2 times, negative 2 times 2, 4. Negative 4 plus 4 is 0. Negative 2 times 0 would be, negative 6 plus 0 is, well, negative and negative makes a positive. 2 times 6 would be, so at this point, it's kind of like, what's the big deal? Because really all we've said is that 0, 2, and negative 2 all work as factors, yes? Okay. Well, if I can expand the page, let's see if I can find it. Nope. There we go. Now we also said what? Because I said that that 2 repeated twice and negative 2 repeated twice. So that means 2, 0, negative 6. I can do this one more time. 2 times 2 is? 0 plus 4 is? 2 times 4 is? Does 2 work again? No, it only worked once, didn't it? So what that means is that negative 2 and 2 actually don't repeat. They don't repeat. And I actually worked this one out ahead of time yesterday and knew it didn't repeat, but somehow forgot. So let's plug back in what we have. Let's see what quadratic we have here. Now, 0 is our constant, or our remainder. 6 is the constant. 0 is the term with x, and 2 is the term with x squared. So really what we have left is 2x squared minus 6 is equal to 0. There's 2 ways to go about solving this. I can use the quadratic formula or the square root method. Either will get us to the correct answer. Or you can just use the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Looking at this here, what is the value of b? 0, because we don't have a x. We don't have an x to the first, so the value of b is 0. So here we just have 0, plus or minus the square root of squared minus 4. Well, a in this case is, and c is, would be negative 6. 2a, well, 2 times 2 is 4. Any questions on any of this here? Any questions on anything we've done so far? For a and, yeah, it's supposed to be a c. Because this is really referring back to our quadratic, basic form of the quadratic, which is ax squared plus bx plus c. And so for us, we had 2x squared minus 6. Since I don't have a b term, since there's not a something times x, b has to be 0. C is going to be this here, and a is just that. So we're never grabbing for this here. We won't grab x. It's just telling us where is a, b, and c. Now, for this here, the 0 up front, what is 0 plus? Is 0 adding anything or subtracting anything? No. So really, I can drop it and just say plus or minus, because 0 plus or 0 minus doesn't change its value. Now inside here, if we simplify what's inside the square root, because negative 4 times 2 is negative 8, and negative 8 times 6 is 48. Over 4. Now if we yeah, because the 4 is negative and the 6 is negative, that negative and negative would make a positive. Now, if we type the square root of 48 in the yellow calculators, graphing calculators will give us a decimal. It'd give us 4 square root of 3 over 4. Well, that would just simplify 2 plus or minus the square root of 3. So there were 2 more solutions. They just weren't whole numbers for this here. Now, one thing I want to point out with this here is that graphing almost gave us all the answers, yes? And that's a good place to start, because if I graph it, I got almost all the answers, and I was able to use those to reduce down to a quadratic, yes? And that's what the goal of most of what we're going to do with all these different methods, is try to find as many of these answers, these solutions as we can to get it to a quadratic. Because if I can get it to a quadratic formula, done. Yes? And that's the goal. That's why we went over synthetic and long division, because they give us ways to simplify the degree down to 2. And we did most of the rest of these here. This is where we stopped, the rational root theorem. The rational root theorem. If we have a polynomial, that's all that says, and has integer coefficients, then every rational solution of f of x equals 0 has the following form: p over q. So for the rational root theorem, I'd write plus or minus p over q, because this is what it is. If it has rational roots, they're going to come in the form of plus or minus p over q. And that's how we kind of list them out. Where p is the factors of the constant term, and q is the factors of the leading coefficient. P over q, the factors of the constant term over the factors of the leading coefficient. Factors of the constant term over the factors of the leading coefficient. And this here will give us every possible rational 0. So if there is a rational 0, a whole number or a fraction, or a mixed number, if we can write it as a fraction or a whole number, this will list it. It will show up in this list. Imaginary and complex. So imaginary solutions are complex numbers or are irrational, so like the square root of 3, will not show up, but it'll give us everything else. Any questions? Oh, let's actually look at this. So we want to find all the real zeros, and we're going to get there. I want to do this here, this listing out the possible rational zeros. So we need to list out our factors of p and our factors of q. Well, p is the factors of what? Because 20. P is our constant term, the factors of 20. Well, the factors of 20 would be 1 and 20. Then we'd have 2 and 10. 30 is not a factor, then 4 and 5. So these are all the factors of the constant term, the factors of 20, yes? Now q is what? The factors of the leading coefficient, the term in front of the variable with the biggest power. Well, what's that number? Okay, I've listed all the factors of 1. Okay. Now, we said all the possible rational zeros come in the form of plus or minus p over q. Yes? So that means I start with q being 1. I start with the smallest cube value, and we're going to divide. So the first one we're going to have is plus or minus 1 over 1. So what's 1 divided by 1? Okay, so we can just, instead of writing 1 over 1, we can just write 1. 2 divided by 1 is 2. 4 over 1. 5 over 1. So plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20 are all of the possible rational zeros for this function. Any questions on this here? We good with this here? Because we're just dividing it by 1. If there were other factors of the leading coefficient, so say it also had 2, well, then I'd go back and do 1 divided by 2, 2 divided by 2, 4 divided by 2, and list out any that we don't have. Now, the pure math way that we're going to, if we were doing this by the pure math book definition, is I would start out with positive 1. So we can do that. Set up my synthetic division. And go 1 for x to the third, negative 8. For x squared, 11 for x, and 20. I would drop the first one. Now, the first number in my list is positive 1. So we do 1 times 1, which is negative 8 plus 1 is negative 7. 1 times negative 7 is negative 7. 11 plus negative 7 is 4. 1 times 4 is 4. Is that a solution? Is that a factor? No, because it doesn't give us remainder of 0. Okay. That didn't work. I'd go on to negative 1. If that didn't work, I'd go on to 2. If that doesn't work, I'd go to negative 2, then 4, then negative 4, 5, negative 5, 10, negative 2, 20, negative 20. And if all those didn't work, I'd have to try something else. Do we have another way to check to see if there are any zeros? If there are any solutions? Well, we did it yesterday. What did we do yesterday? Didn't I use this here? Okay, let's plug this in. So in y equals, clear. Yes, I want to clear. So we're going to do x to the third over minus 8x squared plus 11x plus 20. Once you type it in, hit graph. Once you get it typed in, hit graph. Hey, negative 2, 1, 2, 3, 4, 5, 6, 7, 8. Second table. Hey, actually, negative 1 worked, didn't it? 1 would work. I know it's wrong. Zoom 6. There we go, that looks better. So negative 1 does work, yes? Also 4 and 5. Okay, so now I know some zeros. So what I can do is I can come back here. So I was close. So it wasn't positive 4 that, or positive 1 that works. It actually is negative 1. Well, negative 1 times 1 is, oops, if I have a pen, negative 1. Negative 8 plus negative 1 would be negative 9. Because a negative and a negative would get a bigger negative. Negative 1 times negative 9 would give us positive 9, yes? 11 plus 9 is 20. And negative 1 times 20 is negative 20. Which gives us 0. Would you all agree with this here? Okay. So now I have a quadratic, because we have constant term x and x squared, yes? 3 terms is going to be a quadratic. I can do the division again, because we also said what? It was positive 4, yes? We don't have to rewrite this down below if you want to, because this is what I do when I do the synthetic division. I'll put the cubby hole right next to it and draw a line. Because we're solving it, yes? Does it really matter what these set of terms for the quadratic are? No, we're trying to find out what? What values of x make the function 0? We're just trying to get to the end. So we can do this here. I can just put the cubby hole right there and do the synthetic division again. 4 times 1 is negative 9 plus 4 is negative 4 times negative 5 is negative 20, which would give us 0, yes? Okay. So you see that these two work, yes? I could do it again, but really, what do I have here? Well, this is the constant term, and this is our term with x, yes? So I'm saying what? X minus 5 equals... Can we solve this here? How would we solve this? Add 5. So for us here, x is equal to negative 1, x is equal to 4, and x is equal to 5. Were those 3 listed in our possible rational zeros? Did the calculator also give them to us? Yes. The graphing calculator will give us any whole numbers. What numbers does it not normally give us? Well, complex it doesn't even do. It doesn't do imaginary on the graph. Our square roots of 3, our irrational, doesn't show up well on a graphing calculator. But there's one other. Decimals. So 1/2, 3 and 1/2, 4 and 1/2. Those other fractions that aren't whole numbers, it doesn't show up well. This is where these rational zeros are helpful, because it gives me an idea of what a number should be. And the graphing calculator tells me where it crosses, yes? So if I know about where it's crossing, what it's close to, I can compare it to the rational zeros for those fractions and see which ones work, which ones don't. And we can go from there. So this one's nice and all, and so is this one. I want this one. I want this one. Because I think this one here will be a little bit more interesting. So we're going to solve this one here. I don't find the other two interesting because Q, the factors of the leading coefficient are what? 1 in both cases, yes? So let's actually look at a case where Q isn't just 1. So let's start off with the factors of P. Well, the factors of P in this case would be the factors of 12, yes? So I'd have 1 and 12. Then we'd also have what? 2 and 6. What else is a factor? 3 and 4. get those over because those are all the factors of 12, yes? Okay. Q. We'd have 1 and 10. Because the constant term, or the leading coefficient here is 10. We also have what? 2 and okay. Any questions on how we found the factors of P and Q? Okay, let's find the possible rational zeros. Now again, I'm going to start off with 1, Q being 1, the denominator of this fraction being 1. And if I divide a number by 1, it'll just be that number, yes? Because dividing by 1 doesn't change it. So it'd be 1, 2, 3, 4, bless you, 6, and 12, because 1 divided by 1 is 1. 2 divided by 1 is 2. 3 divided by 1 is 3. 6 divided by 1 is 6. It doesn't change anything, correct? Okay. Let's move on to 2. Well, 1 divided by 2 would be plus or minus, well, we'll leave it as a fraction, be plus or minus 1/2, because it's just 1 divided by 2. What's 2 divided by 2? 1. 2 divided by 2 is 1. Is that up there already? Well, I already have plus or minus 1. I don't rewrite it. If it's already up there, I do not rewrite it. I don't rewrite repeats. Okay, let's move on to the next one. 3 divided by 2 would be, well, plus or minus 3/2, because 3/2 doesn't reduce. That's what it is, yes? What's the next number? Would be 4. 4 divided by 2 is 2. Do we have it? Okay, let's move on. 6 divided by 2 is? We have that? 12 divided by 2 is? Do we have it? Okay, we're done with that one. So I'll start off with 1. 1 divided by 5 would be 1/5, yes? We don't have that. 2 divided by 5 would be 2/5. Then we'd have 3 divided by 5 would be 3/5. 4 divided by 5 would be 4/5. 6 divided by 5 would be 6/5. And lastly, 12 divided by 5 would be 12/5. Because none of those have a common factor of 5. Because it worked out with 2 that 2, 4, 6, and 12 all have a common factor of 2, yes? So they simplify. Any questions on this here? Are we good with this here so far? So let's move to 10. Well, 1 divided by 10 would be 1/10. 2 divided by 10, do they have a common factor? 2 over 10, they have a common factor of 2? 2/10 would reduce down to 1, what? 5th, yes? Do we have that? Yes, okay. 3 divided by 10, well, we have to put that because there's not a common factor. 4 divided by 10, well, that would reduce to 2/5. There's a common factor of 2, yes? 6 divided by 10 would be the same as what? 3/5, because they have a common factor of 2. 12 divided by 10 would be 6/5. And I mean, if you're not comfortable with doing these in your head, you can always type them in a calculator and it'll simplify them for you. I would do them in the yellow calculator, the TI-30XS, because it's a little bit faster to do fractions. Fraction 1 over 10, okay, that's 1/10, we don't have it. Fraction 2 over 10, oh, that's 1/5, we have it. 3 over 10, we don't. 4 over 10 is 2/5. 6 over 10 is 3/5. 12 over 10 is 6/5. Okay, we're done, yes? Because I've used all the factors of Q. We're done. So each one of these here, all of these here, are all possible rational zeros. Graph this thing. Go on and graph it. And let's see what we get. Plus 7x plus 12. You all have this typed in? Yes? Okay. And when you graphed it, it looked something like this here, yes? Okay. So let's look at this here. If I go second table, I look at this table. Back at the graph. Now, one of these spots is a whole number, is it? Well, no, right? So what we do have, and what I do notice, is that it does cross 4 times. Yes? Because it crosses the x-axis once, twice here, and twice over here, yes? So my solutions, I'm going to have 2 positive and 2 negative. 2 positive and 2 negative. Now looking at this one here, this first one coming from the left, this one right here, it is a negative number, so we have a negative. Between -2 and -1, because we have this on a 10 by 10, so each one of these is 1. So I have a value between -2 and -1. That's kind of closer to the -2 side, yes? Because it looks closer to -2. The next negative we have is between -1 and 0. And it's kind of in the middle, yes? That value's close. I mean, it looks pretty close to being exactly right between -1 and 0. I mean, these are just estimations. Would y'all agree with that? The next one is between 0 and 1 and kind of closer to 1. We have a positive between and 1, closer to 1. And the last one is between what? 2 and 3, and it's kind of close to 3. Because unfortunately, the graph didn't tell us anything, but it kind of gives us an idea of where these lines cross, yes? Okay. Let me show you how this is helpful. So let's look back here. This here, y'all would agree with, is a lot of possible answers, yes? Did the graph show us a single time it crossed at a whole number? Now 12, I'm going to tell you, doesn't work. It's actually outside of the graph because we only go from -10 to 10, but 12 is not going to work. So let's look at these fractions. Now, one of the things we did notice Because if I'm looking at these fractions, I have positive and negative 1/2, yes? Hey, is negative 1/2 pretty much almost between negative 1 and 0? It is, isn't it? Okay. Ten. So let's try this here. Because negative 1/2 times 10 would be negative 5. Negative 11 plus negative 5 would be negative 16, yes? Negative 1/2 times negative 16, or negative and negative give us positive. So really we're dividing by 2 and giving us 8. Negative 42 plus 8. Actually will work out to be negative 36. Yes, 34, thank you. I was thinking 6 in my head and I didn't subtract it right. So negative 34. Negative 1/2 times negative 34, negative and negative make a. Positive 17 plus 7 is, well, 1/2, negative 1/2 times 24, it's going to be negative 12. 12 plus negative 12 is 0. So even though it didn't tell us exactly what the value was on the graphing calculator, did it get us close enough using our possible rational zeros to figure it out? Well, yes. So negative 1/2 works. Okay, so that kind of checked the first one off. Sweet. Not that one. Maybe this one. So this one here, we got it. Okay. So what is the degree of this now? It's degree 3, yes? What do I need to get this to? If I can get it to a quadratic, a degree 2, we're good to go, yes? Because then I can use the quadratic formula. So I can look at all of these here and see. So we have one that's close to negative 2, and we have one close to 1, and one close to 3. I'm going to use the one close to 1, because if we're talking about close to 1, we're talking about a number that's very close to the number on bottom. So like a 3 or a 4. Because looking at all this here, 1/2 isn't close to positive 1. 3/2 bigger than 1. 1/5 isn't, 2/5 isn't. So I have a choice between these two and 6/5. So 3/5 is 0.6, 4/5 is 0.8. Let's give it a shot and roll the dice with 4/5. And let's see what happens. Now this here, I would be typing these into the calculator just to make sure. Because if you're not comfortable with doing these, I'd be typing them in. Because 4/5 times 10, well, 10 divided by 5 is what? 2, yes? 4 times 2 gives me 8. Four-fifths times 10 should give me 8. Negative 16 plus 8 is 4/5 times 8. That'd be negative 32/5 because it doesn't simplify. And I have a feeling if we keep going, it's not going to get any better. So I say 4/5 is not the correct one. 6/5 is too big, so let's try 3/5. 3/5 times 10, since we're pushing time, I'm going to just go on and tell you is 6. Negative 16 plus 6 is going to be negative 10. 3/5 times negative 10 is going to be negative 6, because it's the same thing. Negative 40. 40 divided by 5 would be 8. 8 times 3 would be negative 24, which gives us 0. Hey, I have a quadratic now, yes? So the other two spots don't matter. So what I can do is I can plug this into the quadratic formula, negative b. So negative negative 10 would give us a positive 10. Plus or minus the square root of negative 10 squared minus 4 times 10 times negative 40 all over 2 times 10, which would give us 20. Now, negative 10 squared minus 4 times 10 times negative 40 is going to give us 1,700. You can check that at a later time, just to make sure I did this right. And if we simplify this, we would get 10 plus or minus 10 square root of 17 over 20, which is really x is equal to 1 plus or minus the square root of 17 over 2. Is this a whole number? Is this even a fraction? Well, no, because of the square root of 17, it's an irrational number. So that means, really, these two here, or not these two, this one and the other negative would have been irrational numbers. So this here, even though we didn't have negative 1/2 or 3/5 show up on the graphing calculator, we were still able to use the graphing calculator to figure out what they were, because we could see where it crossed and what it was close to. Okay? I'm going to stop